that's all very cool, but how does it actually work? So I'm going to take you through how the audio goes through the whole board and how we are splitting it up and making our LEDs flash. So the first thing we've got is our audio in, and this is going straight into an amplifier. So this is just boosting the voltage that's coming into the board because through the audio cable it's a bit of a low voltage for us to be splitting up, especially when we lose quite a lot when we do that. Right, after this amplifier we are also then sending it back out through the audio output. So this is kind of like a pass-through. And this means that you can hear what you're putting into it, and it's not just going into the board. And so this audio output is so that you can hear the audio that's coming out, and you don't have to put a splitter before you go into the board, which means the board's getting all the voltage of the audio input and it's not being split to the speakers. Okay, so after the amplifier we go into a series of, I'm going to call these the splitters. So we have splitters. So what these are doing is taking the audio input and splitting it into its frequency bands through some passive filters. But they're going to take this, so this is going to create 7 outputs of different bands, frequency bands, and then they're going to go into, I guess, what's technically is an analog to digital converter, so an ADC, and then instead of encoding that output into like bits to store on your computer, we're just turning those bits into LEDs. So we're just flashing LEDs for that. So yeah. Okay. So this splitter is actually kind of 3 components. We're coming in and we've got what's known as a, that's a bit small. We've got what's known as a voltage follower. That's terrible writing. But what that does is stops current flowing through it but keeps the voltage the same. And that just means when we go through the filters, we're not going to be affected by current draw through the filter, and if the current was flowing through the filter, that would just change its kind of frequency response, which isn't great. So that's that. So that's basically our block diagram of the whole circuit, and I'll show you the circuit diagram in KiCad. So this is our kind of circuit diagram. So I'll just explain which blocks of which. So these two, J1, J2, are our audio inputs. So they're 3.5mm audio jacks. Because 3.5mm is left and right channels, we're basically using 2 resistors here to combine into 1 channel. And then this here is a variable resistor, which we're using to change the voltage up and down of the audio input. Why am I doing that? Okay, so we can decrease the voltage coming in because I've done that completely wrong. We've then got a voltage follower. So this is a subsheet in KiCad, just makes it simpler. I only had to design it once instead of 100 times, going into our audio output. We've then got a series of op amps. So this one here is an amplifier, so it's taking our incoming signal, and then it's got a gain of 10, so timesing all the voltages by 10, and then we're going to put it into our 4 voltage followers, so that's 4 in that one, and then 3 down here, into our series of, filters. So this is just this blue wire is all the wires. So we're just taking the output, filtering it, so we're removing the low frequencies and the high frequencies in different bands, and then doing another voltage follower, and then we're putting it into the analog to digital converter. So if we have a quick look in here, this is what an analog digital converter kind of is. So we've got 5 volts up at the top of this resistor ladder here, ground at the bottom, and then between each resistor there'd be a different voltage. So if you've done a potential divider, you just have 2 resistors with a voltage in the middle. But now we've got 20 something resistors, and in between each resistor is maybe half a volt difference. So you can then use that to compare that series of voltages with the incoming voltages, and then we can say if the incoming voltage is higher than the voltage here, we're going to turn on the bottom LED, and then if it's higher than this voltage here, we'll turn on the next LED as well as the bottom one, and that will work all the way up. So if we have a high voltage in this frequency band, we'll have lots of the LEDs on, and so that's where we get the cool effects from. Right, so what we're seeing here is the yellow wave is the incoming signal, and the green wave is what we've amplified. So can I change this on the fly? 1 millisecond. Let's go to 5 micro. Right, so what we're seeing here is we've got an inverting amplifier. So you can see where the yellow wave is below the white line in the middle, we're amplifying the signal negatively. So we're taking a minus 1, timesing it by -5, and we're getting 5 out. That's what's happening here. But unfortunately, when the yellow signal goes above the white line, we're trying to times our 1 volt by -5, and we're trying to push out -5 volts. But because I've only got a single rail power supply and it's running off 5 volts and 0 volts, it's saturating it negatively, and as negative it can go is 0 volts. So what's basically happening is we're chopping off half of our signal, and if you actually listen to the audio output instead of what I've dubbed over it for the video, you can kind of, in a way, hear half the song. So that's my first improvement. So I need to find a way to take our incoming power voltages, take our power, and somehow create a negative voltage from that, so that we can use this amplifier to amplify both sides of the wave, so we get nicer sound coming out of it. Right, so the next kind of issue with this board comes from the voltage drop across the filters. So the green line is coming out of the amplifier here, the first one that we looked at just now, and then the yellow line is coming out of one of the filters, and you can see this green line, the peak goes right off the screen, but down here what's coming out of so what's coming out of the filter down here is a lot lower peak, and that's kind of led to the next issue, which I designed the resistor ladders to have they were all on 1K resistors, but the problem with that is the peak of this yellow signal was about 0.05 volts, but the voltage between these was about 0.1 volts, so it was barely turning on the first LED. So what I've done to fix that is why is there a wire there? Let's just delete that. That shouldn't have been there. Oh, right. So what I've done is basically just replace this 1k resistor with a 680k resistor, and that has basically put a huge voltage drop across this resistor, so that this is now basically 1 volt, and everything below is millivolts apart, which means that we get much more of the signal will actually go to the top of the meter thing, LEDs. So you may have also noticed that the top LED never turns on, because that one's still comparing the original signal with the 5 volts, and that never happens. So I guess the first improvement we could make here was to add the LED before, add the resistor to the top before this first 1k, and that would mean that we'd have the full range. But also what we could do is, instead of just having voltage followers after the filters, we could have more amplifiers, which would also help, because I'm not sure if what's now working, or if we had a voltage with a peak of 3 or 4 volts, I had the gap separation bigger, whether that will give us a better output on the LEDs, or whether what we've got now is working well. I don't know. So that's that. Right, so the other issue that we've got is that if you look at our signal, because we're missing the bottom half of it, right, let's just turn off the yellow one. So if we're assuming this green one is when we're turning on our LEDs, when it's above this dotted line here, what's basically happening is we've got LED on for this section, LED off, LED on, LED off. Right, hang on, I've got a better idea. I'll pop this off. Right, so what we've got is, if we're taking our sine wave like this, and what we're doing is we're converting it into, I'll do this right now. No. We've got our sine wave like this, and what we're doing is we're converting it into this. That's about right. No, we're not. Oh god. We're converting it into, so flat voltage, peak, flat voltage, peak. What's basically happening is the LED, let's say this is the correct this here is the correct frequency to turn the LED on. So we're expecting if we say LED, this is off, this is on, we're expecting it to be like this. What we've actually got is off, on, off, on. So this is just creating a flashy LED that maybe it looks nicer, but we're losing half the signal, we're losing the bottom half of it. So the LED is only on for half the frequency, which is fine if you've got a high frequency. It means it's on more of the time, because if it's a HF, high frequency, we're going to be on, off, on, off. But if we've got a low frequency over here, oh, that's awful, low frequency, then the duty cycle is going to be so you can kind of see it flashing on and off, and I don't know if that's any good. It looks cool like that, but I was thinking that maybe we could, instead of just putting this through because we're going to change this wave, so we can, let's add it in blue, so we can, if we get the amplifier that can amplify both sides, we're going to end up with this. But of course, we're still going to end up with something like this, because the voltage follower only listens to the positive side. So what we'd need to do is we need to fully rectify the signal. So instead of taking this signal here on the left, we need to take the rectified version, which is going to basically flip all the negative voltages into positive voltages, so that we then end up with this. Oh, that's terrible drawing. And then we put that through the ADC. We're going to end up with a much smaller off time. So instead of the whole thing being off, this whole distance, we're only going to have a very short distance, and that's going to be much better. I think the LEDs will be on instead of flashing, and I don't know which is better, which will look better, but I think I should at least try this and see how it works, but add in a way to turn it on and off on the board. I think that's that. The other final improvement that I'd like to do from making this board is this PCB. So ignore that one of the chips is missing, but this was kind of my first design. When I first designed it, this chip here was upside down, so it was like that. So the pin 1 was up at the top, but I'd put all the other ones with pin 1 in the bottom left corner. So then when I soldered this one on, it was upside down and it was backwards, so it like got hot, overheated, burnt itself all up, and then shorted between power and ground, which was not good. So that's that. Also, what was the other thing I was going to say? I'm so forgetful. It was labeling. So it's like here, I had to keep checking which one was +5 and which one was ground. So if I just put on the board in the silk screen plus and ground, that would make it so much easier. I like labeling the input and the output for the audio jacks. I should have done that, and I guess this is me learning from the first time that I've done a board that labeling stuff is a very good idea. So yeah. I don't think there was any issues with this part for the board. There was a few missing traces because when you do the DRC thing, oh, yeah, okay. I was looking at problems, and there aren't any problems, but you can see there's missing traces on the board. I didn't realise there was a tab called Unconnected Items, and so I had the boards printed with a few missing traces, which I had to put bits of wire on the back. So it wasn't a pain, but it's these like little learning things that you don't know about them until you've got it wrong, and then now I've done it, it's so much easier. Right. So thank you for watching this short demonstration of the boards that I made that came out way bigger than I was expecting. But I've definitely learned a lot from this, and I even managed to get myself a fancy oscilloscope thing. So it was a cheap one that plugs into my PC, but it does exactly what I need it to do. So that's good. So thanks for watching, and maybe I'll see you soon with the next version. Thanks.